Okay, so today we're going to be talking about identifying and sketching quadric surfaces. So, what is a quadric surface? A quadric surface is just a type of surface in 3D space, and its general equation is ax squared plus by squared plus z squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus j is equal to 0. So, we're gonna be go over ring six basic types of quadric surfaces: ellipsoid, hyperbola of one sheet, hyperbola of two sheets, elliptic cone, elliptic paraboloid, and hyperbolic paraboloid. Okay, so since I don't really know how to draw this whiteboard, I'm gonna use decimals to demonstrate a lot of my graphs. So let's talk about ellipsoid. The general equation for ellipsoid is x squared plus y squared plus z squared is equal to 1. X, Y, and Z are divided by some number. So let's say 1, 2, 3. And also the number below has to be squared. So in this case, Z would be something like root 3 squared, and this would be root 2 squared. So, this is an ellipsoid. It looks like an oval, or when the bottoms are ones, it's going to become a sphere. So if this is one, and this is one, it's going to become a sphere. So how do we analyze these traces and draw them? So I'm not going to be drawing them, but we're going to be using something called traces. So traces is when you just analyze the 3D object by just two axes. So if we can see here, this is the XY trace. We don't have the Z value here, so this is going to be a 2D object. So we're going to be observing this 3D object from three different angles. So this is the XZ trace. This is the XY trace I just mentioned. And if we flip this over, it's going to be the YZ trace. So, how do we analyze these traces with the equation? So, let's look at x squared plus y squared plus z squared. So, this is the XZ trace. What that means is there is no y here. So, y is going to be 0. We can just ignore y here. So, we have x squared plus y squared is equal to 1. The bottom number doesn't really matter. It just changes what the axis is going to be. So, x squared plus z squared is equal to 1. So, this is going to be a sphere or an ellipse here in the xz trace. Let's look at the yz trace. Y squared plus z squared is going to be another ellipse or sphere if we look at just on the yz axis. For the xy axis, it's pretty much the same thing. There's no z, so x squared plus y squared is equal to 1. So let's talk about hyperbola with one sheet. So this is going to be a bit different from the ellipsoid. Okay, let me zoom out a bit. Okay, this is good. Uh, let's just analyze the traces. Let's look at the XY trace. There is no Z value here, so it's just going to be x squared plus y squared is equal to 1. So as we can see here, there's going to be an sphere or ellipse looking thing like this, the outside. So this is the XY trace. So let's look at the YZ trace. Oh, let's look at the, yeah, YZ trace. There's no X here, so YZ is Y squared minus Z squared. There's no X here. It's going to be a hyperbola. So yeah, the outside looks like a hyperbola. And let's analyze Z trace. There's no Y here, so it's going to be X squared minus Z squared. Much like the YZ trace, this is going to look like a hyperbola too. So this is why it's called hyperboloid of one sheet, because there's only one sheet of ellipse. Okay. Well, actually, one sheet is because it's just one object. There's no cuts in between here. You're gonna see in hyperbola two sheets. So Let's talk about hyperbola of two sheets. This one is going to be quite similar to hyperbola of one sheet as, okay, this is a hyperbola of one sheet. Let's analyze the traces. In the YZ trace here, there's no X, so it's going to be Z squared minus Y squared. I just don't want to move it over, but Z squared minus Y squared is equal to 1. So this is another hyperboloid. Same with the XZ trace, because it's another minus X, so Z squared minus X is equal to 1. So this is a hyperboloid. I mean hyperbola. And the interesting thing about hyperboloid of two sheets is the XY trace. So there is no Z value here. It's just X squared minus Y squared. So, uh, there is the X squared minus Y squared. So we have minus X squared minus Y squared is equal to 1. So since there's going to be since this is minus, we can factor out the minus 1 here. So it's going to be minus, in parentheses, x squared plus y squared is equal to 1. And so, however, since we're not talking about in 2D, the x squared uh, plus y squared equals to minus 1 doesn't really matter because there's still a z value here that can flip the, the minus 1 here into a positive number. So this thing can be an ellipse here. It's just gonna be no graph when z is equal to 0. So as you can see here, z equal to 0. If, if there's no z here, uh, x squared plus y squared is equal to minus 1, and that is not a valid graph. So it's just gonna have values for some values of z here. So let's talk about elliptic cone. Elliptic cone is another one of those x squared, y squared, z squared. And this one is, I'd say it's quite similar to hyperbola of two sheets. So it's going to be x squared plus y squared minus z squared is equal to 0. So we can see here, this thing kind of looks funny. It's like an x, and we're looking at the xz trace here. So x squared minus z squared is equal to 0. So this is a kind of a weird hyperbola. If you think about it. If you zoom in more, it's gonna look more like a hyperbola. But since this is 0, not 1, it's gonna have some funky stuff here. So this is hyperbola. And yz trace, same thing here. Y squared minus z squared. It's gonna be some funky hyperbola. And xy trace, it's much like the hyperbola of two sheets. Since there is no z here, it's gonna be x squared plus y squared here. And since z is going to be like some integer here, the right side is never going to be 0, except for when z is equal to 0, in which we can see here there's no graph for z is equal to 0. So it's going to look like an ellipse. So for elliptic paraboloid, this one is quite different from the ones we've seen so far, because instead of z squared, it's going to be just z now. So as we can see here, there's no negative z value because x squared plus y squared is always going to be a positive number, so z cannot be a negative number here. So let's analyze the yz trace. Okay. We have y squared is equal to z, which looks like a very flat parabola because the parameters here are kind of wacky. So it's going to be a parabola here, but I hope you guys can see that this is a parabola. And same thing for xz trace. It's just x squared is equal to z. It's also a parabola. Pretty standard stuff. And for the XY trace, let me zoom out a bit more. Yes. If we zoom out a bit more, x squared plus y squared is equal to z. Z is some integer, so x squared plus y squared is equal to 1. It's going to be an ellipse or circle. So this is elliptic paraboloid. Hyperbolic paraboloid is pretty similar. We just have to add a minus here. So x z trace, it's minus x squared is equal to z. So we have the negative upside down parabola here. So ignoring y, z is equal to minus x squared. It's going to be upside down paraboloid. For yz trace, there's no x, so y squared is equal to z. It's a up parabola. And for xy trace, let me zoom out a bit. It's going to be y squared minus x squared equals to some number here. So it's going to be a hyperbola looking thing. So it isn't hyperbola. Okay, so that's all 6 of the common uh, quadric surfaces we're going to be seeing in multivariable calculus. And I'm going to show you guys how to classify and sketch the surface. Okay, so let's look at a problem from the Larson textbook. Let's look at number 29 since I don't really have time for the one, but this one is a really challenging one and it's going to require a lot of algebra skills. So let me rewrite this as 16x squared plus 9y squared plus 16z squared minus 32x minus 36y plus 36 is equal to 0. So every time we have x squared, y squared, z squared, there's a constant next to it. We gotta factor that out first. So we have just x squared, y squared, and z squared. So we're gonna use them completing the squared. So 16x squared minus 32x plus some number here, uh, and then plus 9y squared, minus 36y, and then plus some number here, and then plus 16z squared, just plus 36 is equal to 0. Okay, so we're gonna factor this out. We're gonna use the x minus y whole squared formula here. So it's gonna be x squared minus 2xy plus y squared. So the x here is 4x, so actually I should use AB here, but you get the point. So it's gonna be 4x and this number here. So divide by 4x, it's gonna be 8 here, 8, 2, so y is gonna be 4. So 4 squared is gonna be 16. Why this is 4 squared? Uh, why is it like that? Because if we factor 16 out, it's gonna be x squared minus 2x plus 1, and that's gonna be x minus 1 whole squared. So actually factoring out might be a better strat here. So this is 16 x squared minus 2x plus 1. So let's factor this out first. 936, it's pretty nice. 9y squared minus 4y. This is 2xy, so the y here is going to be 2. So this is going to be plus 4. So this is plus 36 over here. And then, so 16z, just leave it like this. Let's move the 36 over to the other side. So it's going to be minus 36 plus the 16 here and plus the 36 over here. So let me make space for this. So the right hand side is going to be just 16. Left hand side is going to be 16 x squared minus 2x plus 1. It's going to be x minus 1 whole squared. And y squared minus 4y plus 4 is equal to y minus 2 whole squared. Whole squared. You just leave 16 z like this. Okay. So we want the right side to be 1, so we have to divide all sides by 16. 16, 16, 16. So it's gonna be x minus 1, I really ran out of space here, squared plus uh, y minus 2 whole squared over 16 over 9, because this is 9 over 16, so if we divide on the bottom, it's going to become 16 over 9, plus z squared over 1 is equal to 1. So, since we have plus plus here, we know that this is going to be an ellipsoid, and since we have minus 1, minus 2 here, we know that there are transformation in 3D objects, so the the center of the ellipsoid is going to shift to 1 uh, on the x axis and then 2 on the y axis, and no change on the z axis. And as for axes, we know the y is going to be 16 over 9 whole square, so the axis is going to be 4 over 3 long. It's 4 over 3 whole square is the axis. And for two of these, both x and y, it's going to be 1, because 1 squared is equal to 1. So let's graph it on our trusty Desmos. So I'm just gonna input the entire equation here, since we already solved it and transformed it into a standard form. So it's gonna be equivalent. Or how to do that? 16 x squared minus 32x minus 36 y plus 36 is equal to 0. Okay, so let us zoom in. It's very, very fast. So, as we mentioned here, the center is gonna be 1, comma 2, comma 0. Let's see. Center is x is equal to, this is 1. I kind of reversed it, so 1. This is the center, 1, comma 2, comma 0. So, our center is right. And let's check our axes. X-axis is 1 unit long. From 1 to 2, it's going to be 1 unit long. For z, it's also 1 unit long, because this is 1 here, so it's going to be 1 unit long. And for y, it's going to be 4 over 3 units long. So we can't really see here, but it's like 1 plus a bit more. It's going to be 1/3. So that is basically how we uh, identify and sketch graphs. Quadric surfaces. Okay, that's it.